Imagine being a researcher staring at a massive neural network, wondering how on earth it's making decisions. You're trying to understand the inner workings of this complex system, but it's like trying to read a black box. This was exactly the problem researchers faced when they started working with large language models. They could see the inputs and outputs, but what was happening inside was a complete mystery. Can we understand how large language models reason? A paper in Communications of the ACM highlights this issue. It's a question that has puzzled many in the field of AI and ML. So, what happens when researchers try to open up a neural network? They're essentially trying to peek inside the black box to see how it's making decisions. One approach they've taken is to look for what's called a global workspace. This concept, introduced in a paper by Anthropic, suggests that there's a central hub in the network where information from different parts is integrated. It's like a meeting room where all the different departments come together to discuss and make decisions. But how do they actually find this global workspace? It's not like there's a map that says, "Hey, the global workspace is over here, come check it out." To find it, researchers have to use various techniques, like analyzing the network's architecture or visualizing how data flows through it. It's a bit like being a detective, searching for clues and piecing together the evidence to figure out what's going on. And when they finally do find the global workspace, they can start to understand how the network is making decisions. But that was not the real problem. The real problem was understanding how the network was using this global workspace to reason and make decisions. This is where mechanistic interpretability comes in. It's an approach that tries to explain how a neural network works by breaking it down into its individual components. It's like taking apart a machine to see how all the different parts fit together. By doing this, researchers can start to understand the underlying mechanisms that drive the network's behavior. For example, they might find that the network is using a particular circuit to recognize patterns in data, or they might discover that it's using a sparse autoencoder to compress and reconstruct data. But why does this matter? It matters because if we can understand how a neural network works, we can start to trust it more. We can use it in situations where the stakes are high, like in healthcare or finance. And we can also start to improve it by identifying areas where it's going wrong and fixing them. This is especially important in fields like preclinical research, where AI-driven virtual cell models are being used to simulate the behavior of cells. A paper in Nature highlights the potential of these models, but also notes that they need to be validated and translated into clinical practice. Now, you might be thinking, what does this have to do with neuroscience? Well, it turns out that the techniques used in mechanistic interpretability are similar to those used in neuroscience. In fact, the field of neuroscience has been influencing the development of machine learning and vice versa. It's a two-way street, where ideas and techniques are being shared and adapted. A paper in the Transmitter, called Trading Places, explores this intersection between neuroscience and machine learning. But here's the thing. Most explanations of mechanistic interpretability focus on the what, not the why. They'll tell you about the different techniques and tools used, but they won't explain why they work the way they do. They won't give you the underlying cause of the behavior. And that's what's really important. If we can understand why a neural network is working in a certain way, we can start to predict how it will behave in different situations. We can start to anticipate its strengths and weaknesses. For example, let's say we're using a neural network to recognize images. We might find that it's using a particular circuit to recognize edges and shapes. But why is it using that circuit? Is it because it's been trained on a particular dataset that emphasizes those features? Or is it because the circuit is somehow inherent to the network's architecture? If we can understand the why, we can start to design better networks that are more robust and reliable. And that's where the concept of causal tracing comes in. It's a technique used in mechanistic interpretability to identify the causal relationships between different components of a neural network. It's like tracing the flow of causality from the input to the output to see how the network is making decisions. By doing this, researchers can start to understand the underlying mechanisms that drive the network's behavior. But what about the potential applications of mechanistic interpretability? How can it be used in real-world scenarios? Well, one area where it's being used is in the development of more explainable AI systems. These are systems that can provide insights into their decision-making processes, so that users can understand why they're making certain recommendations or predictions. It's a key area of research, especially in fields like healthcare, where transparency and trust are essential. And if you're interested in learning more about mechanistic interpretability and its applications, be sure to subscribe to this channel. We'll be covering more topics like this in the future and providing insights into the latest research and developments in the field of AI and ML. By subscribing, you'll get access to exclusive content, including videos, articles, and podcasts, all focused on helping you understand the complex and fascinating world of artificial intelligence. Now, let's take a step back and look at the bigger picture. Mechanistic interpretability is not just a technique, it's a way of thinking about neural networks. It's a way of understanding how they work and why they make certain decisions. And it's an area of research that's rapidly evolving, with new techniques and tools being developed all the time. So, if you're interested in staying up to date with the latest developments, be sure to follow this channel. But here's a common misconception about mechanistic interpretability. Some people think it's just about understanding how a neural network works, but it's actually about understanding why it works. It's about getting to the underlying causes of its behavior and using that knowledge to improve it. And that's what makes it so powerful. By understanding the why, we can start to design better networks. Networks that are more robust, more reliable, and more transparent. And finally, let's talk about the potential risks and challenges of mechanistic interpretability. One of the biggest challenges is the complexity of neural networks. They're highly complex systems with many interacting components, and understanding how they work can be a daunting task. But the potential benefits are well worth the challenge. By developing more explainable AI systems, we can start to build trust in these systems and use them in situations where the stakes are high. So, to sum it up, mechanistic interpretability is a powerful tool for understanding neural networks. It's a way of breaking down complex systems into their individual components and understanding how they work. And it's an area of research that's rapidly evolving, with new techniques and tools being developed all the time. By understanding the underlying mechanisms that drive neural network systems, systems that are more robust, more reliable, and more transparent. And that's what makes mechanistic interpretability so exciting. It's a field that's full of possibilities and full of potential for innovation and discovery.